Okay, I think we can get started. Good morning, everyone, and welcome to the GISS Sea Level Rise Seminar. We're very glad to have Dr. Kaitlin Naughten. She is an ocean ice climate modeler at the British Antarctic Survey, and she specializes in ice shelf, ocean, and sea ice interactions around Antarctica. Her research primarily focuses on the response of the Antarctic ice shelves to climate change and the implications for global sea level rise. She co-developed the UA-MIT GCM, one of the world's first successful coupled ice sheet ocean models, and is now developing ice sheet ocean coupling in the UK Earth System model. Dr. Naughten earned her PhD from the University of New South Wales, Australia, and her bachelor's degree from the University of Manitoba in Canada. And the subject of her talk today will be unavoidable future increase in West Antarctic ice shelf melting over the 21st century. Welcome.
That's great. Thank you so much, Patrick, and thanks everyone for having me here today. Thanks for the introduction. As Patrick said, my name is Kaitlin Naughten. I work at the British Antarctic Survey in Cambridge. For those of you who don't know me, I have a bit of a stutter, so if you could just be a bit patient. Sometimes it takes a while to get the words out. These are some exciting and depressing results, which were published a few months ago in Nature Climate Change, and actually received quite a lot of media attention, which was an experience indeed. So I'm excited today to dive into these results in a bit more detail than the newspapers were able to cover them. So why do we study ice sheet ocean interaction? As I think probably most of the audience here knows, ice ocean interaction has huge potential to cause sea level rise from Antarctica. On one hand, this is just because it's quite a lot easier to melt ice using water than using the air, but also because the oceans around Antarctica are quite a lot warmer than the atmosphere. So how much of the ice is actually vulnerable to ocean-driven melting? Basically, if the ice is grounded on bedrock, which is below sea level, so that's all of the blue regions in this figure here, that has the potential that someday the ocean could melt its way underneath the ice sheet and essentially melt it from the bottom up. And by area, that's over 40% of the Antarctic ice sheet. So that's quite a lot of ice that we're concerned about. And the key processes here are ice shelf cavities, which are the little pockets of ocean in between the ice shelves and the sea floor. So you have ice, ocean, and then rock. And what happens in these little pockets of the ocean will be absolutely crucial in determining the future of global sea level rise. What's the temperature in these cavities? Well, what's the salinity? What's the circulation doing? And this is hard to model. Happens at quite small spatial scales. The geometry changes over time. And as recently as 2013, ice-ocean interaction was so difficult to quantify its contribution to sea level rise that the IPCC was essentially excluding it from its calculations. So this has improved a bit since 2013, and we have some estimates of what ice-ocean interaction could do, but it's still one of the leading uncertainties in projections of future sea level rise. So what do we see in observations? In observations, West Antarctica seems to be changing quite rapidly. We can see from satellites that West Antarctica is losing ice, and this loss is accelerating. West Antarctica is responsible for almost all of the sea level rise from Antarctica. There's a small contribution from the Antarctic Peninsula, and East Antarctica is very slightly growing, so very slightly offsetting the loss elsewhere. And when we look into the details of how this melting is spread out spatially, we can see that is linked to ice shelf thinning in the Amundsen and Bellingshausen seas. So today I'm going to focus on the Amundsen Sea over here. So Pine Island Glacier, Thwaites, Dotson and Crossan, Getz, then over on things like Cosgrove and Abbott. All of these ice shelves over here are thinning, and that is the driving factor behind the sea level rise. Obviously, ice shelves don't directly contribute to sea level rise, but if you thin an ice shelf, in almost all cases, the glaciers behind that ice shelf will speed up their flow towards the ocean. And that's what causes sea level rise. You cannot explain this ice shelf thinning without invoking the ocean. And so it's clear that the ocean is causing these ice shelves to thin from underneath. I'll just also say Zoom seems to be cutting off the edges of my slides, and so some of the references for these figures are cut off. If you have any questions about where the figures that come from, I just ask at the end or send me an email. I'm happy to share all my sources with you. So you would think that if an ice shelf is being thinned by the ocean, that implies that the ocean is warming. That isn't actually clear to us because we don't have enough observations to confirm whether the ocean is warming in this region. You can't measure ocean temperature at depth using satellites. You have to send in a ship or a CTD or floats or submersibles or some sort of in situ observation to see what the ocean temperature is actually doing. And this part of the world is so hard to get to that these sorts of observations only started in 1994. And since then, they've been very limited in both space and time. And that lack of observations combined with a very high interannual variability in this region is quite strongly affected by things like ENSO, and so it's always sloshing back and forth between a warm state and a colder state. And that short record and high variability means that we cannot detect a significant trend. It doesn't mean that the ocean hasn't been warming. It's just we haven't been looking at it for long enough to know for sure. So instead, all we can do is to run simulations with models to see if it makes sense that the ocean would form in response to the atmospheric changes that we've seen over the last century. And that's exactly what I did in my second to last paper a couple of years ago, running a regional ocean model with ice shelf cavities, forcing it with our best estimates of what the atmosphere may have done over the 20th century, finding that indeed the ocean temperature warmed in response at the sort of mid-depth level, which matters most to the ice shelf cavities, and also the ice shelves melted in response. So that, if it's true, would explain the ice loss that we've seen in observations. the obvious next question is, how might these processes change in the future? And it turns out that we have surprisingly few future projections of these sorts of processes of ice shelf melting in West Antarctica, given how important a process that this is for sea level rise. And again, the lack of future projections is down to the fact that this is quite hard to model. The Amundsen Sea is hard to represent well in certain Antarctic or global configurations. So one reason for this is you generally have to have quite high resolution. So we have a few Antarctic-wide projections of ice shelf melting, but we don't really trust what they do in the Amundsen Sea in the present day. So why should we trust what they do in the future? Recently, there were the first future projections using a specialized high-resolution model of the Amundsen Sea, but these only looked at the worst-case scenario, RCP 8.5, which is quite an extreme scenario, as I'll get to. And they also didn't examine the role of interannual climate variability, which we know is very important in this region. So what I've tried to do in this study is to have a really comprehensive look using one model of how the system could change in the future, looking at the worst case scenario, RCP 8.5, but also the best case scenario where we limit warming to 1.5 or 2 degrees global average under the most ambitious aims of the Paris Agreement, and then scenarios in between. And for each scenario, looking at internal climate variability. So that means from running ensembles of 5 to 10 members each, which sample different timings of modes of variability, like ENSO and the IPO, which we know are important in this region. So here I'm using a global climate model output from CESM to force a regional ocean model of the Amundsen Sea at the surface and also at the lateral ocean boundaries. So this regional ocean model is MITGCM. It is just this little box of West Antarctica here. It has ice shelf melting, but the ice shelves are constant in shape over time because we don't have a coupled ice sheet model. It also has interactive sea ice. And so adding up all of these different scenarios and ensemble members, in total I've run over 3,000 years of simulations. So that's a nice amount of data to do some statistics with. And what I want to know with all of these different scenarios is how much ice shelf melting is now unavoidable, regardless of how much we reduce fossil fuels, and how much do we still have control over with mitigation, and also how long before the different fossil fuel scenarios start to diverge before we start to see the results of our actions. But the results are not very cheerful. In all scenarios, we see a widespread warming of the continental shelf. So here's an example of 2 degrees warming scenario. So following the sort of median goals of the Paris Agreement. The black dotted line shows the continental shelf break. So everything south of that is the shallower bit of the ocean, which interacts directly with the ice shelf cavities at mid-depth, which I'll talk about later. So there's a very obvious widespread warming here, and also an increase in ice shelf melting essentially everywhere. So plotting up all of the different warming trends in the ocean in red and ice shelf melting trends in blue across all the different scenarios, so historical and for different future scenarios. This is a box plot. So every set of box and whiskers shows the ensemble spread and the median and the mean of each ensemble. And the first thing to see here is that the rate of change in the future scenario, so for the 21st century, is quite a lot stronger than over the historical period in the 20th century. Even in the best case scenario, in a 1.5 degree global warming scenario, the rate of change of ocean temperature and ice shelf melting increases by about a factor of 3. The other thing that we can do is to compare the different ensembles in the different scenarios and see if the differences between them are statistically significant. And we find that the trends in the 3 lower range scenarios, so 1.5 degrees, 2 degrees, and RCP 4.5 are all statistically indistinguishable from each other. So with the exception of the highest fossil fuel emissions scenario, RCP 8.5, mitigation seems to have very limited impact on the size of the trend over the next century. The main determinant of the exact magnitude of warming in a given simulation is in fact internal climate variability. Just changing the ensemble member of the atmospheric forcing can change the size of the trends by up to a factor of 2. And obviously internal climate variability is something that we have no ability to control or on any reasonable time scale to predict. If you instead plot up these scenarios as a time series, so starting with historical and then branching off into the different future scenarios, you can see that the 4 future scenarios are quite strongly overlapping for the majority of the 21st century. RCP 8.5 eventually diverges from the others, but this is only significant beginning in 2045. Here I'm looking at essentially a window of the rolling means of each time series, and the point of divergence is 2045. So that's another couple of decades from now, and now is already over here, in which mitigation, even if the worst case scenario doesn't have a significant impact. Something else to notice here is that the 1.5 degree scenario starts to flatten out by the end. And so even though the trend isn't significantly different from the other scenarios, the rolling means of the 1.5 degree scenario do start to diverge in about 2059. So we think that if these simulations were continued into the 22nd century and beyond, that the scenarios would start to spread out a bit more. But on the time scale of the 21st century, the differences are very small, if anything. So now let's talk about the oceanographic processes which are causing this ocean warming. So let's start by looking at some temperature profiles averaged over the continental shelf of the Amundsen Sea. So just looking at this left panel here, this is a temperature against depth, and you can see that there's a colder layer on top, which we could call winter water, and a warmer layer underneath, which is circumpolar deep water. It's unusual in the global ocean to have cold over top of warm, but the reason this happens is that at colder temperatures, density is almost entirely determined by salinity. And so it's a cold and fresh layer over a warm and salty layer. And they're separated by this steep transition called the thermocline, which is essentially the boundary between the warm and the cold water. So this boundary moves up and down over time as the volumes of these two water masses fluctuate. And this shows up as a peak in the standard deviation right around the depth of the thermocline. Here, I've also highlighted the depth range of 200 to 700 meters, which I analyze in a lot of the other figures. This corresponds roughly to the average depth range of ice shelf cavities. So at 200 is the average ice shelf draft, and 700 meters is the average bathymetry at the ice front. So whatever happens in between these depths is the most important to the ice shelf cavities. So the first and most important process which is causing warming in these simulations is that the volume of this warm circumpolar deep water is increasing. You can see this most clearly at the height of the thermocline. So the gray line here is historical, and the colored lines are the future scenarios. And this transition between warm and cold is bumped up slightly. And this also shows up in the warming trend is strongest just around the transition. So it isn't that the water masses themselves are changing so much, it's that their volumes and their positions are changing relative to each other. So why is the volume of circumpolar deep water increasing? It's increasing because there's increased transport of it onto the shelf. Circumpolar deep water is essentially north of the Atlantic deep water, which is upwelled in the Southern Ocean. You see it offshore all around Antarctica, but it only comes onshore in a few specific locations. Again, one of these locations is the Amundsen Sea. On the continental shelf, there's a system of troughs. The Dotson get trough over here, the Pine Island Thwaites East trough over here, where this warm water flows on shore. And what we can see in the simulations is that all of these existing pathways where the warm water comes on shore are speeding up. Essentially, the velocity is increasing, the transport is just increasing. I've highlighted a couple of cross sections here. On the Dotson gets trough, you can see the Amundsen undercurrent, which flows along the shelf break from west to east. It's trending eastwards, so it's speeding up. And similarly, the flow onshore through the Pine Island Thwaites East trough is also speeding up. It's becoming stronger towards the south, which you can see in this big blue spot over here. This second process, which causes a small amount of warming, is the loss of convection. So over the historical period, we simulate occasional cold convective events where the water column overturns, the thermocline drops almost all the way down to the sea floor, and that cools and ventilates the circumpolar deep water. You can see the influence of this convection in the fact that the gray line is just a bit cooler than all of these future scenarios, and also the standard deviation is elevated at depth. The peak isn't just in the thermocline, it's also lower down. This convection completely disappears over the course of the historical and early part of the future scenarios. And it disappears because the surface is freshening and stratifying, so it's harder for the water column to overturn. And so the loss of these cold mixing of events also causes some of the warming at depth. Here I've plotted up some Hofmüller plots, showing depth against time. The left column is the temperature anomaly with respect to historical, and the right column is the standard deviation. You can spot convection when the standard deviation is elevated at depth. So this basically says that at least one ensemble member is convecting at any time when you see these big purple blobs dropping below about 500 meters. Over the historical simulation, convection happens about 10% of the time. Keep in mind, this is an ensemble. In the future simulations, it happens less than 1% of the time. It completely disappears. There's a few members which convex slightly at the beginning, but that's all gone by 2030, depending on the ensemble member. But we know that while this process is interesting, it isn't the main cause of the warming. If you exclude all of the periods of convection, the historical warming trend changes by about 24%, but the future warming trends change by less than 3%, depending on the scenario. So even when the convection is gone, the warming continues as the volume of circumpolar deep water increases. The final process I want to talk about is specific to RCP 8.5, and that's really just an extension of the first process by which the volume of CDW increases and the thermocline shoals. But it shows quite a lot more in RCP 8.5, so in the pink compared to the other future scenarios. And crucially, the thermocline and the peak of the standard deviation becomes so shallow that it no longer strongly affects the depths of the ice shelf cavities. So that this means that while there is still a variation in the balance of warm and cold waters, that variability is so shallow that the ice shelves barely feel it. And instead of switching back and forth between warmer cavities and cooler cavities, they're just always in a warm state. So while this isn't a separate process oceanographically, it is an important state change for the cavities themselves. The next obvious question is which atmospheric drivers are causing these changes in ocean temperature, specifically the speeding up of the undercurrent and increased transport of circumpolar deep water onto the continental shelf. A lot of previous literature was focused on the winds, specifically the winds at the shelf break. In some historical analyses, there had been a correlation in between the strength of the zonal winds over the shelf breaks, so stronger winds toward the east, or rather an anomaly towards the east caused the shelf to form. But that isn't what we see in these simulations. And some other research in my team at BAS is also calling into question the hypothesis that winds at the shelf break are the most important driver. Because if that were true, we would expect that the scenarios with more eastward winds, or rather stronger eastward trends in the winds, would show stronger warming on the shelf. And that isn't what we see at all, because some of the future scenarios have very minor changes in the winds as the ozone hole recovers, and yet the ocean temperature still can continue to increase very rapidly. So if you plot up the correlation at every point in between trends in the winds and trends in ocean temperature on the continental shelf, the correlation, first of all, isn't significant over the shelf break, but even if we ignore significance, it's going in the wrong direction. So this doesn't mean that zonal winds aren't important. It just means that the story isn't as simple as we used to think. And the correlation is quite a lot stronger and quite consistent with atmospheric thermodynamics variables, like surface temperature and precipitation. So it looks like the drivers of these changes are primarily thermodynamics, but obviously this is just correlation, it isn't causation. Untangling causation is a big question. I have a student working on this at the moment, so we're hoping to understand better how the the exact atmospheric drivers impact the undercurrent over time. So what all the journalists kept asking, which I kept having to tell them I couldn't give them an answer, is how much sea level rise are we looking at in response to the changes I've simulated. Unfortunately, since we don't have a coupled ice sheet model, we cannot quantify this. Obviously, basal melting, although it's the main driver of ice loss currently, you cannot translate that into sea level rise estimates directly without also knowing what the surface mass balance is doing and what the ice sheet dynamics are doing in response, and that means a coupled ice sheet model, which is something that we're working on. But what we can do is to look at the spatial distribution of ice shelf melting and ask ourselves if it qualitatively looks like it would be important for sea level rise. Because not all ice shelves are created equal. Some are more important than others in terms of their ability to cause sea level rise. So here I've plotted up something called the buttressing flux response number, which is essentially the ratio of ice discharge across the grounding line in response to ice shelf thinning in a specific location. So all you have to know is the larger the number, the more sea level rise would result if you thin that specific area of the ice shelves. So the most important regions are some of the deep grounding lines, as well as some of the shear margins, including Pine Island and the middle of Thwaites. Whereas other regions in yellow and white have much lower impact, and some regions in blue actually have a negative impact. So grounding line flux slows in response to ice shelf thinning in some specific locations, but overall the grounding line flux increases. So what I've done is I've plotted up the ice shelf melting trends I simulated as function of this buttressing flux response number. So on the left is ice shelf melting trends in the regions which provide less buttressing, and on the right is the regions which provide more buttressing. And as you can see, the curves are relatively flat, meaning that all ice shelf classes melt more than before. The less important ice melts more, but so does the more important ice. And something else I want you to see is the difference between scenarios. So here comparing RCP 8.5 in pink to the rest. The differences in between scenarios are disproportionately among the less important ice. So the gap over on this side is quite a lot larger than over on the right side. And this makes sense oceanographically, because the real difference in RCP 8.5 is that the last little bit of extra shoaling of the thermocline, which disproportionately affects a shallower ice, which usually has lower buttressing. So that says that the ability that we still have to control future changes in ice shell melting based on mitigation, the only bit that we really have control over is concentrated among the ice, which doesn't even matter so much for sea level rise. So in summary, my simulations suggest that we are likely committed to a rapid increase in the rate of ocean warming and ice shelf melting over the rest of this century. Mitigation by reducing fossil fuels has a very limited impact. In fact, the only scenario which is statistically distinct from the others is the worst case scenario. And our global fossil fuel emissions are already trending away from this scenario to the point where it could be argued it's no longer a realistic possibility. And we cannot quantify what this means for sea level rise in our study without an ice sheet model, but it isn't likely to be good. Ocean warming would really only accelerate the changes that we've seen so far in satellite estimates of ice sheet mass loss. And the main uncertainty in our simulations is that they only use one model. Obviously, in climate science, we like to use multiple models whenever we can. At this stage, the modeling technology just isn't quite there yet to be able to do these sorts of studies with a lot of different models. So someone had to be the first, and it was us. But I would really like to see over the next few years for these sorts of experiments to be repeated with multiple models, so we can have a sense of how much agreement or lack thereof there is structurally. Some implications for policy. I think this study really highlights the importance of adaptation, because it suggests that further sea level rise from West Antarctica is inevitable. Sea level rise isn't going to stop or slow down while West Antarctica continues to warm in the ocean, and our studies suggest that the driving factor will only speed up. And so I think it's time globally to start thinking seriously about how we are going to deal with continued and accelerating sea level rise over the next few centuries. This doesn't mean that mitigation is useless. Obviously, mitigation is important for so many reasons, not the least. West Antarctica is only one cause of sea level rise, and sea level rise is only one impact of climate change. But for this, a specific impact of climate change, mitigation might have limited power to change the outcome, at least over the next century. So after 2100 is when we can probably still make more of a difference to the rate of change in this region of Antarctica. And thank you so much for listening. I'm happy to take questions. I'm also happy for anyone to send along an email if you want to chat further. Thanks very much.
Very much, Kaitlin. Do we have any questions?
Shaina.
Hey, great talk. Thank you. Do you think there are any negative feedbacks that maybe not captured in this modeling system that might make things seem a little bit better? Maybe I'm kind of clutching at straws a little bit.
So if you're thinking about geometrical feedbacks between the ice sheet and the ocean, there's evidence for both positive and negative feedbacks. An example of positive feedback is as you melt an ice shelf and the grounding line retreats, you increase the area of ice which is exposed to the ocean. So even if the rate of melting spatially average stays the same, the total melting integrated over the ice shelf increases as the area increases. But there are also examples of negative feedbacks. The classical one is that here, let me bring up some of those profiles again. So you have the cold water over the warm water, and the ice drafts sit around 200 meters at the ice front, and they deepen as you enter the cavity. But let's say at 200 meters, as an example, if you melt the ice shelf and it thins, then that ice ocean boundary will rise up in the water column, so that the ice is typically exposed at a colder water. So all else being equal, shoaling of the ice draft is negative feedback if you assume that the structure of the water column stays the same. Does that make sense?
But I guess I'm asking, do you think that these negative feedbacks might impact some of the projections in a way that would maybe make things seem less dire?
It's hard to tell.
Yeah.
I was a co-author on a sort of process study, which included an ice sheet model. So looking at ice ocean coupling in the Amundsen Sea, but on it's sort of an idealized configuration, and it found that the sign of the net geometrical feedback varied from ice shelf to ice shelf. So in some ice shelves, the influence of having a coupled ice sheet with evolving geometry increased the total ice shelf melting, and then the next ice shelf over, it would decrease. So it's hard to tell whether the estimates would go up or down if you were to account fully for these feedbacks. I don't think it's clear one way or the other.
I have a question. Maybe it's slightly off topic, but when you think about Antarctica and the ice shelves, like last year's sea ice, like crazy, you can't help but think of that. In any of the experiments that you looked at, like how common was that large of a retreat of the sea ice extent? And can we tell, like, regardless of scenario, like how frequent does it occur in the Paris 1.5s or the RCP 8.5s?
Yeah, so I didn't do a lot of detailed analysis of sea ice extent. I mostly looked at the rates of melting and freezing of sea ice. I think if you're looking at any kind of sea ice study, you should first of all have a circumantarctic model, because something that we often see in observations is that the different regions offset each other. So, for example, you'll have a retreat of sea ice in the Amundsen and Bellingshausen Sea. This is my region of study. At the same time, you'll have an expansion of sea ice in the Weddell Sea. So I don't think that this configuration is as a good tool to study sea ice. I am involved in another project, which is looking at sea ice in a global couple models, and the questions you ask are exactly what we're trying to understand is how often do these sorts of sea ice loss events occur? Are they influenced, and to what extent are they influenced by anthropogenic forcing? And what are the underlying drivers in terms of modes of circulation and all of that. So it's early days. I don't have any results to share, but if you keep an eye out on what vast science is up to over the next few years, hopefully we'll have some answers on that front.
Super, thanks.
Thank you.
Any other questions? Well, I guess there are no questions. We can stop there.
Thank you so much, everyone, for having me.